You know, it's wild to think about, but an artificial intelligence query takes roughly 10 times the electricity of a standard internet search.
Oh, yeah. It is a massive jump.
Right. And when you multiply that by the millions of generative AI tasks happening every single hour, this quote-unquote weightless cloud suddenly requires enough raw metal, water, and power to sustain a small city.
It really is a complete paradigm shift. I mean, we spend so much time talking about algorithms and software, but the moment you introduce advanced AI and massive data sets, you collide directly with the unyielding laws of physics and physical infrastructure.
Which is exactly why you, the listener, are here with us today. You are prepping for a really significant challenge, and today's deep dive is laser-focused on conquering the foundational technical concepts of the HPE0-S59 exam.
Absolutely.
We're going to strip away all the magic of the cloud and look at the real physical and architectural mechanisms that actually make modern AI infrastructure possible.
And just to set the baseline for you, based on the parameters of the HPE0-S59 exam, you're looking at a 1 hour and 30-minute test.
Okay, good to know.
Yeah, and it consists of 50 multiple-choice questions, which, by the way, include both single and multiple responses. You'll need a 61% to pass, and the exam is delivered in English, Japanese, and Korean.
Perfect. So here is the mission for today's session. We're going to do a step-by-step, question-by-question deconstruction of 10 critical practice questions.
This is the best way to learn, honestly.
I agree, and the format rule we are following is simple but crucial. I am going to read the full text of every single question and all 4 options, A, B, C, and D, completely aloud, word for word. Then we break down exactly why every option is either the perfect fit or a carefully disguised trap.
Because, in an architectural exam, understanding the mechanical reason an option fails is really the only way to truly validate the correct choice.
Okay, let's unpack this with question 1. We are starting with the biggest macro decision an IT architect makes. Where does the sensitive data physically live?
Right, the foundational question.
Exactly. So here's the question. A healthcare provider wants to implement advanced analytics to process medical images, but is strictly prohibited from moving patient data off-site due to regulatory compliance. Which solution strategies should the architect propose?
Okay, let's hear the options.
The 4 options are A hybrid approach moving only anonymized metadata to the public cloud. B, a centralized software as a service analytics platform hosted by a third party. C, a distributed computing model relying solely on end-user workstation hardware. D, a fully contained private cloud infrastructure deployed within their secure facility. To me, this data restriction sounds like a high-security vault. The gold can never, ever leave.
Yeah.
But how do you run heavy processing algorithms? You can't send the data out to an established public cloud.
Well, basically, you build a processing engine inside the vault. Let's look at the mechanical failures of the other options first. Option A, the hybrid approach with metadata, is a total trap.
Wait, really?
Oh.
Even just the metadata?
Oh, yeah. I mean, in strictly regulated healthcare environments, data sovereignty laws often dictate that even scrubbing the data and moving anonymized metadata violates compliance. The gold cannot leave the vault in any form.
Wow, okay.
And option B fails for the exact same reason. A third-party SaaS platform fundamentally routes protected data through external servers.
Okay, I see why external fails, but what about option C, just processing it on the doctor's local computers?
Yeah, so option C fails on hardware constraints. I mean, medical imaging AI models like analyzing high-resolution MRI scans require hundreds of gigabytes of video RAM to process effectively.
Oh, wow.
Exactly. A standard end-user workstation will literally crash trying to load the model into memory. Which brings us to the correct answer, option D.
The fully contained private cloud.
Right. It keeps the compute, the storage, and the AI resources physically on premises. It acts as a localized, high-performance engine governed entirely by internal audit protocols. So the knowledge point here is private cloud for regulated AI workloads.
Got it. So you've decided you have to build this massive engine inside your secure vault. But how do you actually assemble an AI-capable private cloud without, spending 6 months troubleshooting software drivers?
That is the million-dollar question.
Right. And that brings us to question 2. Which statement best describes the fundamental value proposition of a co-engineered private cloud solution designed for generative workloads?
Okay, hit me with the options.
Here they are. A, it replaces all physical hardware with containerized virtual instances. B, it focuses exclusively on optimizing basic business analytics processing. C, it outsources all data governance responsibilities to public cloud vendors. D, it delivers a turnkey, validated full-stack environment that accelerates deployment.
Interesting.
Wait, I need to push back on this premise a little bit. As an architect, wouldn't it be much more customized and therefore much more powerful if the customer just bought all the separate infrastructure components themselves, like pick the fastest storage, the newest network switches, the best servers?
On paper.
Yes.
In reality, building an AI cluster from discrete parts often results in a massive, massive integration nightmare.
Really? It's not just plug and play.
Not at all. It's not just plugging things in. It's like ensuring the firmware of a specific network interface card communicates flawlessly with the storage controller's operating system under maximum load.
Ah, I see.
So let's eliminate the distractors. Option A is physically impossible. I mean, containers require physical metal. Option B is incorrect because we are specifically discussing heavy generative AI, not lightweight business analytics.
Right.
And option C just outright violates the core premise of a private cloud, since governance must stay in-house.
Leaving us with D.
Exactly. Option D is the correct answer. The mechanical value is a turnkey, validated full-stack environment.
So what does co-engineered actually mean in that context?
Co-engineered means the vendor has already spent thousands of hours in a lab ensuring every piece of firmware, virtualization layer, and hardware component is perfectly matched and pre-tuned for AI workflows. You completely bypass the integration friction.
So you just move straight to deploying models.
Precisely. The knowledge point is co-engineered AI infrastructure solutions.
Okay, so once that turnkey stack is powered on and ready to go, let's look at the actual data flow, specifically for massive tasks like large language models. Question 3. For a customer building a large language model from scratch, what architectural component requires the highest synchronization and scaling capability?
This is a fun one.
The 4 options are A, the northbound network connecting to the public internet. B, the localized database utilized for logging user telemetry. C, the interconnect fabric bridging multiple graphics processing units across nodes. D, the cold tier storage utilized for retaining historical system logs.
Okay.
I imagine this like trying to coordinate a massive symphony. Like every single musician needs to hear exactly what the others are playing in real time, or the whole piece just falls apart.
The symphony analogy works perfectly, but let's look at the instruments themselves. Training an LLM requires breaking a massive mathematical problem into thousands of pieces, solved simultaneously across hundreds of GPUs. So options A, B, and D handle administrative, external, or cold storage tasks. They operate on standard networking timescales, which might tolerate a few milliseconds of delay.
But the GPUs can't tolerate that delay.
Not at all, which is why option C is the correct answer. The interconnect fabric bridging multiple graphics processing units across nodes.
Because they have to talk to each other so fast.
Yes. GPUs must exchange calculated gradients and model parameters millions of times per second. If you force that communication over a standard network, the GPUs spend more time waiting for data than actually calculating it.
Oh, wow, that's a huge bottleneck.
Exactly. You require dedicated low-latency technologies like InfiniBand or specialized NVLink fabrics that physically bypass the central CPU to share memory instantly. The knowledge point is high-performance GPU interconnect technologies.
So we have hundreds of GPUs firing parameters back and forth at the speed of light, but all that microscopic data movement generates immense physical friction, right? Which triggers a massive real-world crisis for the facility.
It absolutely does.
Which leads to question 4. As a data center scales its deployment of dense computing nodes, which facility constraint often becomes the primary limiting factor requiring architectural redesign?
Let's hear the choices.
Option A, maximum cable length limits for standard serial connections. B, the number of available rack units in standard cabinets. C, the ability to deliver sufficient power and extract the corresponding thermal output per rack. D, the maximum supported distance for standard single-mode fiber optics.
Right.
It's just wild to me that at this cutting-edge level of software intelligence, the primary roadblock is basic thermodynamics.
It always comes back to thermodynamics. Always. Let's address the logistical options first. Option A, serial cable limits. Option B, physical rack unit availability. And option D, fiber optic distances. Those are all solvable logistical issues.
Like you can just buy your way out of them.
Pretty much. If you run out of rack space, you lease another row. If a cable is too short, you route it differently.
But you can't just route around heat.
Exactly. Option C is the correct answer. The ability to deliver sufficient power and extract the corresponding thermal output per rack. A traditional data center rack might consume 5 to 10 kilowatts of power,
Okay.
but a single dense AI rack can draw 40 to 100 kilowatts. You cannot physically push enough chilled air through the server chassis to cool chips running that hot.
So what do you do?
It requires a complete facility redesign to bring direct-to-chip liquid cooling and massive specialized power distribution units directly to the server racks. The core knowledge point is power and cooling requirements for AI data centers.
Okay, so now you have a dense, power-hungry, liquid-cooled cluster. It's stable physically, but how do you keep it stable from a software perspective without breaking everything?
The operational nightmare.
Right. Question 5. To maintain optimal stability and security in a dense cluster of accelerated servers, what is the recommended approach for applying system updates?
The options are going to be interesting here.
Here they are. A. Applying updates individually to each server during peak business hours. B. Utilizing defined baseline profiles to ensure uniform compliance across the entire server group. C. Disabling all automatic update mechanisms and relying purely on manual intervention. D. Outsourcing the update process to end-user application developers.
Okay, yeah.
Wait, if I push a standardized update to an entire dense AI cluster simultaneously, aren't I risking breaking a multi-million-dollar system all at once if the update has a bug? I put off updating my laptop for weeks out of fear.
Yeah, that is the exact fear that drives bad practices, which we see in the distractors here. Option A, applying updates individually, creates what we call configuration drift.
What does that mean practically?
It means server 1 is running different driver versions than server 100, which basically causes parallel processing to crash. Option C, pure manual intervention, is just operationally impossible at scale.
And option D?
Option D is absurd. And user developers write applications, they do not manage infrastructure firmware.
Right, so how does option B solve the fear of breaking the whole system?
So option B is the correct answer. Utilizing defined baseline profiles. A baseline profile is a strictly validated combination of firmware, BIOS, and OS versions known to work perfectly together.
Ah, so it's tested beforehand.
Exactly. You don't necessarily reboot the whole cluster in the same millisecond. You do a phased rollout governed by that baseline. This guarantees that when a server comes back online, it perfectly matches the uniform compliance of the group. It prevents the drift that causes silent failures. The knowledge point is infrastructure baselines and update management.
Makes sense. But before you even worry about managing updates on the system, you have to buy the right size hardware in the first place.
Very true.
Question 6 focuses on the sizing phase. During the initial sizing phase of an infrastructure project targeting advanced analytics, what is the most critical metric to capture from the customer's existing data science team?
Let's see them.
The 4 options are A, the specific software frameworks and the expected size of their datasets. B, the preferred brand of desktop monitors used by the developers. C, the total number of generic office productivity applications in use. D, the physical dimensions of their administrative office space.
This is a classic exam question.
I am looking at these options, and frankly, knowing the brand of desktop monitors or the dimensions of their office space seems hilariously irrelevant to an infrastructure architect.
It is. But as an architect taking this exam, you have to recognize test strategy. The exam writers include these seemingly absurd options to test your focus.
Really, just to mess with you.
Yeah, if you lack confidence, you might second-guess yourself like, oh, maybe high-resolution monitors require specific remote desktop GPUs. You have to ruthlessly ignore end-user noise. Options B, C, and D have absolutely zero impact on back-end compute calculations.
Which isolates option A. But why are the frameworks so critical?
Option A is the correct answer. The specific software frameworks and the expected size of their datasets. Different frameworks, like TensorFlow versus PyTorch, map memory, and utilize GPU tensor cores in mechanically different ways.
Oh, so the software literally changes how the hardware runs.
Exactly. Knowing the framework dictates your hardware acceleration compatibility. Additionally, the dataset size dictates the physical width of the data pipeline you need to build. The knowledge point here is AI infrastructure sizing and workload analysis.
Okay, so let's say you mapped everything perfectly to their frameworks, deployed the liquid-cooled servers, but the system just stalls.
It happens more often than you'd think.
Question 7 touches on this. A data science team reports that their newly deployed high-performance servers show unusually low accelerator utilization during model training. What is the most probable architectural cause?
And the option.
Option A. The external firewall is dropping incoming web traffic requests. B. The storage subsystem is unable to feed data to the computing nodes fast enough. C. The virtualization hypervisor is operating with excessive memory overhead. D. The cooling infrastructure in the data center is running at maximum capacity.
Right.
If the GPUs are showing low utilization during an active job, does that basically mean they're just sitting around starving for data?
Starving is the perfect architectural term. Let's look at why the others don't cause starvation. Option A, firewall drops. Well, those affect external users, not internal model training.
Right, the training is already inside.
Exactly. Option C, hypervisor memory, and option D, maxed out cooling, will absolutely cause system throttling or crashes. But they don't cause a healthy GPU to simply sit idle while a training job is running.
So the data just isn't reaching them.
Correct. Option B is the answer. The storage subsystem is unable to feed data to the computing nodes fast enough.
Why does that happen?
Think about the mismatch. A modern GPU uses a PCIe Gen 5 bus that can chew through gigabytes of data in a fraction of a second. If your storage subsystem is running on legacy protocols or spinning disks, it's like trying to fill a swimming pool through a drinking hose.
Wow.
The GPU finishes its tiny calculation and then just sits idle, wasting thousands of dollars an hour in electrical costs. The knowledge point is storage bottlenecks in AI training environments.
Everything we've discussed so far assumes a pristine, highly controlled data center. But what if the data is being generated and needs to be computed out in the real world, like at the base of a remote cell tower?
A completely different ballgame.
Question 8 addresses this. When designing a computing solution for a remote telecommunications cell tower, which design constraint typically takes precedence over raw computational performance?
Okay, let's hear the option.
Option A, extended operating temperature ranges and specialized physical form factors. B, integration with enterprise-grade identity management systems. C, support for the maximum number of multi-tenant virtual machines. D, compatibility with legacy desktop operating systems.
Yeah, the answer here is pretty stark.
Choosing an edge server over a data center server feels like, I don't know, choosing a rugged off-road vehicle instead of a Formula One race car because you're driving through a muddy jungle.
It's even more extreme than that, honestly. It's not just that the Formula One car gets stuck in the mud, it's that an edge server literally doesn't have the luxury of a 70-degree clean room.
So the environment is the enemy.
Always. Let's clear the distractors. Option B, identity management. Option C, virtual machines. And option D, legacy OS, are all software considerations. Software does not matter if the motherboard melts.
You can't outcompute the 110-degree heat wave.
Exactly. Option A is the correct answer. Extended operating temperature ranges and specialized physical form factors. At a cell tower, the server is subjected to extreme heat, vibration, and dust.
So how does it survive?
The system must physically throttle its own CPU just to keep from failing. The passive heatsink essentially replaces the gigahertz. Environmental survivability entirely dictates the architecture. The knowledge point is edge computing and ruggedized infrastructure.
Okay, let's bring the data back from the edge to the high-performance cluster. If we are relying on Ethernet to carry these massive internal workloads, we can't just plug standard networking cables in and hope for the best.
Absolutely not.
Question 9. In a high-performance clustered environment, utilizing remote direct memory access over Ethernet, what network switch capability must be carefully tuned to ensure optimal performance?
All right, what are the 4 choices?
Option A, standard spanning tree protocol convergence timers. B, dynamic routing protocols for external internet access. C, priority-based flow control and data center bridging enhancements. D, wireless access point density and signal strength.
Okay, deep networking here.
I really need to understand the mechanism here. Why isn't standard internet protocol good enough for this internal cluster?
Because standard internet protocol like TCP/IP is specifically designed to be forgiving.
Forgiving. So?
Well, if a network switch gets overwhelmed, it just drops the packet, and the sender eventually realizes it and resends it. In a microsecond-sensitive AI cluster, resending data destroys the entire parallel processing timeline.
Oh, I see.
So option A, option B, and option D are traditional networking concepts that actually tolerate those drops.
But we can't tolerate the drops. We need something that prevents them entirely.
Right. Option C is the correct answer. Priority-based flow control, or PFC, and data center bridging enhancements.
How does that prevent drops?
To run remote direct memory access, or RDMA, over Ethernet, you need a lossless environment. PFC mechanically works by monitoring the microscopic memory buffers inside the network switches. Just before a buffer overflows and drops a packet, PFC sends a microsecond pause frame back to the transmitting server, basically holding the data on the wire until the switch can process it.
That is incredible engineering.
It really is. The knowledge point is RDMA and data center networking optimization.
This brings us to the final hurdle. No matter where this hardware is deployed, whether it's a rugged box at a cell tower or a liquid-cooled RDMA-tuned AI cluster, how do you guarantee the hardware itself hasn't been secretly compromised at the factory before the operating system even loads?
The ultimate security question.
Question 10. At the hardware level, what technology provides the foundational security mechanism for modern enterprise servers deployed in sensitive environments?
Let's hear the options.
Option A. Software-based intrusion detection systems running in the operating system. B. An immutable silicon fingerprint verified during the boot process. C. Network perimeter firewalls inspecting all incoming traffic. D. Physical lock and key mechanisms on the server chassis front bezel.
Right.
Just to clarify, we aren't talking about standard antivirus software here, right? We are talking about security mechanisms physically baked into the metal.
Yes, exactly. We are trying to prevent firmware-level attacks that hide underneath the operating system. Option A, intrusion detection. Well, that fails because it boots with the OS way too late to catch a compromised motherboard.
Makes sense.
Option C, network firewalls. They only scan network traffic, not local firmware. And option D, a physical lock, only stops someone from, physically stealing the hard drive. It doesn't stop a digital supply chain hack.
Which isolates the silicon itself. Option B.
Option B is the correct answer. An immutable silicon fingerprint verified during the boot process.
How does that actually work?
This is known mechanically as a hardware root of trust. During manufacturing, a unique cryptographic hash is physically burned into the silicon. The exact millisecond the server receives power, it checks the firmware against that burned-in hash.
And if it doesn't match?
If the math doesn't perfectly match, the silicon just refuses to hand over control to the BIOS. It cuts off the attack before the cooling fans even spin up. The knowledge point is hardware root of trust and enterprise security.
Thanks for joining us on this deep dive.
Best of luck in your exam. Keep questioning mechanics.